This is the lesson for section 2.6b, the greatest integer function. As you can see from our PowerPoint, a common piecewise defined linear function is the step function. In a moment, I will give you a chance to graph the piecewise defined function to see what I mean. A step function always consists of horizontal segments arranged like steps. That's why it's called a step function. The greatest integer function, the function we're going to look at today, is a special step function. But before we get too far ahead of ourselves, let's take a look at the next slide. I would like you to pause the video and graph the function you see below. It's written as a piecewise defined function, and it has three pieces. In all cases, notice that f of x, or y, is equal to a constant value, but it's defined to be in different ranges of value of x. So see what you can do with that, and then resume the video in a moment and see what our graph looks like. So now you can resume the video, and if you take a look, I have graphed the function, the piecewise defined function for f of x, which, as you can see, looks like a series of three horizontal segments. One occurs at -3. You can see that one here below, right here. And then the second one, where f of x equals -1, appears here. And then the third one, where f of x equals 2, appears here. Notice the left endpoint for all three of these steps is an open circle. And that's because in the inequality conditions, you can see the left inequality symbol is a strictly less than, and when you flip that inequality around, when f of x equals -3, x has to be greater than -4. And then when f of x equals -1, x has to be greater than -1. And when f of x equals 2, x has to be greater than 3. So the left endpoint is an open circle. The right endpoint, however, is a closed circle, and that's because the inequality symbol on the right end of our compound statement is less than or equal to. And so that's going to appear as a solid dot, and you can see when f of x equals -3, the right endpoint is a solid dot at -1. And then when f of x equals -1, we have a solid endpoint at +3. And then when f of x equals 2, on the right end, we have a solid dot where x equals 5. So our graph looks like a series of three horizontal steps, as you can see there. As far as the domain and range, if we wanted to talk about the domain of our function is going to be values, all of the values that occur between -4, because the first step where y is -3, we start at -4. It doesn't include -4, but it does include everything from -4 to -1. And when we're at -1, the next step when you jump up to it, even though it's open circle on the left end, because it's a solid circle on the right end of the previous step, we include where x is -1. And then on that middle step, we get all values of x between -1 and +3, including +3. And then when you jump up to the next step where y is 2, it does not include 3, but that's okay because it's included on the previous step, and that gets all values of x between 3 and 5, inclusive of 5. So for our domain, I could say f of x is equal to, or the domain is equal to x such that, and I'll write it in compound form, -4 is less than x is less than or equal to 5. So really we're saying x is greater than -4, but less than or equal to 5. It's an and if you separate those two inequalities and write it as x is greater than -4 and x is less than or equal to 5. So that's our domain. Then we want to talk about our range. Our range is where the steps occur for y. And so in this case, our range only occur at 3 distinct values. If I list them in order, it's -3, and then -1, and then +2. And those are the y values where each of our steps occur. Our steps are not connected vertically, so there are no other values of y. So that's our range. All right, now let's introduce to you the greatest integer function. It is also a step function, but we write it using a little different notation. And you can see on our next slide, it says the greatest integer function notation is as you see it. That's read f of x equals the greatest integer less than or equal to x. You can see how it's defined that way right here. And so I've put a number line there so you can think about this. But for all real numbers x that you enter into the greatest integer function, it always returns the largest integer that is less than or equal to x. In essence, it rounds down a real number to the nearest integer. So for example, you can see below, if I input a +1, the greatest integer less than or equal to 1 is 1. But if I input 1.5, which on a number line is right about here, the greatest integer less than or equal to 1.5 is also 1. If I enter 3.7 approximately here, the largest integer less than or equal to 3.7 is 3. If I enter 4.3 about here, the greatest integer less than or equal to 4.3 is 4. Notice it's always the integer to the left unless you evaluate an integer like the greatest integer less than or equal to 1 is that integer. So let's be careful with negatives. If I evaluate the greatest integer less than or equal to -2, that's an integer, so that's going to evaluate as -2. What if I evaluate -1.6? That'd be about here. So the greatest integer less than or equal to -1.6 would be -2. How about -2.1? Slightly to the left on the number line. Well, the greatest integer less than or equal to -2.1 is -3. And if I evaluated -5.5, which is off my number line, it would go to the next integer of -6. So you get the idea of how the greatest integer function evaluates. So then moving down, I am showing you what the greatest integer function graphs like. It graphs like a step function. Think about it. If I put in 0 to the greatest integer function, the greatest integer less than or equal to 0 is 0. So my table would fill in like that. At 0.5, the greatest integer less than or equal to 0.5 would also be 0. When I evaluate the next integer of 1, the greatest integer less than or equal to 1 is 1. If I enter 1.2, it will also evaluate as 1 because that's the integer that's to the left and the largest integer less than or equal to 1.2. If I enter 2, it would be 2. If I enter 2.7, it would also evaluate as 2. the largest integer less than or equal to 2.7. If I enter negative 0.5, that's going to evaluate as negative 1. That's the largest integer less than or equal to negative 0.5. And if I evaluate negative 1, it would be negative 1. So if I try to start graphing, you have to understand at each integer, a new step is starting. I usually start with positives when I test values, or 0 I actually start with, because we think better when they're positive or 0. So 0 is my starting place, and you can see here I have a solid dot at 0 because the greatest integer function returns 0 when you enter it, but values to the right of 0 are going to evaluate as 0 as well until you get to the next integer of 1. And when you hit 1, you jump to the next step, which is right here. The right end of the step before it is an open circle because when we reach 1, it actually evaluates as 1, so we jump up to the next step. At 1.2, we'd still be on the step where it's 1 because 1.2 is somewhere in between 1 and 2. But then when I reach 2, the right end of that step becomes an open circle because I jump up to the next step where the input is 2 and it evaluates as 2. Of course, 2.7 would be on that step because the greatest integer less than or equal to 2.7 is 2, and you start to see the pattern. Once you establish the pattern, you can just copy it forward and backwards. And just so we see backwards, when I put negative 0.5, that evaluates as negative 1, which is right about there on that step. At negative 1, that's an integer, and the greatest integer less than or equal to negative 1 is negative 1. So that is the start of a step, and you can see right here the solid dot there. But once you reach 0, which is way at the top of my table, that's where we jump up to the next step. So the steps rise from left to right on the parent graph. As far as the domain, you have to think of like the game of Tetris, where all the steps kind of trickle down to the x-axis. And what I'm trying to get you to visualize is where one step ends with an open circle, the next step begins with a solid circle. And so all these steps are end to end, and it really fills in the entire real number line for the x-axis, which means the domain is all reals. The range, on the other hand, the steps are not connected, but the steps all occur at the integer values, so you can see each step occurs at an integer. So that's the parent graph and how it works. And all other greatest integer graphs are related to this parent graph. Now, we can make tables of values to help us graph these, but once we start to understand transformations, that will help with us getting this table of values as well. So if we look here and I start entering values, for each of these functions, if I put in 0, the greatest integer less than or equal to 0 is 0, and 0 times negative 2 is 0. If I put in 1, 1 times negative 2 is negative 2. If I put in 2, I get negative 4. If I put in 3, negative 6. If I put in 4, negative 8. Now, I haven't tested integers in between, but I want you to compare that to the actual graph. When I put in 0 for h of x, 0 minus 5 is negative 5. 1 minus 5 is negative 4, negative 3, negative 2, and negative 1. So what I want you to do is take a look at these graphs, try them on your own, and then compare them. And I want you to see if you can notice what's happening in each of the graphs. The negative 2 is actually making our steps go down if you compare to the table of values. And when you look at the range actually occurs at all even integers. And then if you look at this second graph, it shifts the parent graph original step at the origin 5 units. It's actually, in this case, shifting it 5 units right the way it's written, because it's written here, well, I can use that one. It's written like this because it's in the greatest integer bars. So I know you think it's going 5 units down. 5 units down is written like that. It happens to be with the greatest integer function, they're the exact same graph. Because if you look at this parent step, I can move it 5 units to the right, which is h of x, or if I move it 5 units down, that's what I've called g of x here. So that's what I want you to notice. The homework is right here on the worksheet 2.6. On side page 38, you're going to try 5 and 6. On side page 39, 3 and 4. We'll tie up loose ends on Monday when I return. Have a good day.